Hello, my name is Alejandro Jenkins. I'm a professor of physics at the University of Costa Rica. Some weeks ago, I gave a talk on the challenge of active dynamics in theoretical physics. This was a talk intended for other professors and the students at the department. This was part of the celebration of the 50th anniversary of the department at the university. And now I would like to revisit that talk. I've made a few adjustments, and most importantly, I'm now giving this talk in English rather than Spanish in order to record it and make it available in my YouTube channel. Here I would like to give a general overview of my main research interest in the last few years. I'm a high energy physicist by training, but most of what I'll be discussing now seems to be rather far away from high energy physics, even though at the end I'll mention um, some recent work that I've been doing on how some of these ideas might be applied in cosmology, in the description of the very early universe. So what do I mean by an active system? What do I mean by the term activity? Well, first, let me remark that as far as any physicist thinks, all of physics is ultimately reducible to four fundamental forces of nature: gravity, electromagnetism, and the strong and the weak nuclear forces, all of which are presumably conservative forces. So the law of conservation of energy is exact. However, many macroscopic phenomena of interest are not just non-conservative, they're actively non-conservative. And by these, I mean that there is a force that does positive work when it acts on some object that moves along a closed path or trajectory. And here's a video that a friend shared with me some years ago of his dog playing with a ball. And here you see that at one point the ball just rolls down under the action of gravity. So that's not mysterious. Gravity is a conservative force described by a potential. So the gravity will go down in gravitational potential until it reaches some local minima, and then it would stay there. But here the dog is intervening and it's picking up the ball and it's returning it to a higher position from which it can roll down again. And the dog could repeat this over and over. And you can confuse students, I've done this in my time, by pointing out that the dog, presumably, is still everything that the dog does is reducible to this conservative fundamental forces of nature, particularly in the case of the dog. Its interaction with the ball is entirely electromagnetic, in fact, electric. But then how is it that the dog is acting non-conservatively on the ball? There is no, as far as we know, dog is not a fundamental force of nature that can be added to these others. Um, so where does its ability to do net positive work over a closed path of the ball come from? And this is a question that turns out to be of great practical importance. But what I would like to emphasize is that I don't think it has ever been really adequately incorporated into the scheme of theoretical physics. And this is the challenge that I want to raise. Active dynamics is behind the persistence of cycles, say in engines. Engines run cyclically. The engine in a car, the pistons in the car go up and down, but after they return to their original position, they've done some net amount of work which has been moved to move the car forward. And living organisms, of course, there are also many persistent cycles, the heartbeat, the respiration cycle, and so on. And as I will emphasize in a minute, actually the whole scheme of analytical mechanics as it was developed in the 18th and the 19th century of analytical classical mechanics, and which was the same scheme that was later used in the 20th century to develop quantum mechanics, the quantum mechanics of closed systems, is not applicable to this kind of active systems. And it's not applicable because these active systems have a disequilibrium persistent disequilibrium, which is associated with a positive feedback. I'll have more to say about this. But I would like to help motivate this with a historical anecdote. Some of you might have heard this story, but I don't think its significance has been widely appreciated, at least not in this context. It's a story about Leonhard Euler. Euler, of course, was one of the most important, most productive modern mathematicians, as well as a very significant theoretical physicist, and indeed one of the fathers of analytical mechanics. The story is that Euler had been working for some time at the Academy of Sciences in St. Petersburg, the capital of Russia, but due to a change of government and a conservative backslash, the foreign scientists were expelled from Russia. So Euler ended up in Berlin, where King Frederick II of Prussia, or better known as Frederick the Great, was establishing a new Academy of Sciences. But it turned out that the relationship between Euler and Frederick was strained from the beginning. They didn't like each other. And there's a famous letter that Frederick wrote years later to his friend, the French philosopher Voltaire, in which he complains that I wished to make a fountain in my garden. So he's saying here is that he wanted to build a nice monumental fountain for the garden at his palace in Sanssouci, in Potsdam, outside of Berlin. This was to be in imitation of the fountains in the gardens of the Palace of Versailles outside of Paris. At the time, the royal court in Prussia was very much looked up to the court in France as a model to imitate. And Euler, who was at the time a leading member of the Russian Academy of Sciences, was asked to help out with this process. So Frederick says the Cyclops, or Euler, he calls him a Cyclops because Euler had lost an eye to an infection. And later on, he would actually go entirely blind, but this did not affect his productivity in any significant way. The Cyclops Euler calculated the effort of the wheels, that is, the wheels in the hydraulic pump, needed to raise water to a pond, that is, to a reservoir, from which the water was to descend by canals to make the jet of the fountain at the Palace of Sanssouci in Potsdam. And then Frederick goes on to say, my mill was built mathematically and could not raise a single drop of water to within 50 feet of the pond. Vanity of vanities, vanity of mathematics. So here he's saying that Euler might have been a great mathematical genius, but he proved useless at the task of helping him to build a working fountain in his palace. This is a picture of the palace of Sanssouci in Potsdam nowadays. So you see that now there is a big fountain in the garden, but presumably this was built some time later because the project in Frederick's lifetime failed. Now, I had heard this story. At some point, out of curiosity, I looked for some literature in the history of science on this subject, and I found some articles by a historian of science in Germany, Eckert. In these articles, Eckert actually defends Euler, and he says that it was not his fault that the project failed. There were other problems that Frederick was too stingy and he hired incompetent engineers. And he cites, Eckert cites in defense of Euler, the fact that he published several papers at around this time, calculating the work that was necessary in order to raise a column of water at a certain velocity, at a certain height, including the effects of friction from the motion of the pipe and the motion of the water in the pipes. But my attention was immediately struck by the fact that Euler described the action of the hydraulic pump in this way. So he imagines a piston that is being pushed down by a force, capital K, and he'll equate that force capital K to the weight of an imaginary column of water of height little k. So it pushes down on the piston, and then that squeezes the water out of the cylinder and through the pipe and up to the reservoir. And he calculates the value of K that is needed in order to do this at a certain height, a certain velocity, with some given amount of friction. So the calculation that Euler does is correct, but his description of the operation of a hydraulic pump is completely unrealistic, because this is not how a hydraulic pump works at all. A hydraulic pump is a cyclical engine, so it has either a reciprocating piston or a turning wheel, and the piston goes through a full cycle of its motion, or the wheel does a full turn, and at the end of that, it has done some amount of work on the water, which is capable of raising it to the reservoir. But this cyclical active mechanism of pumping falls outside of the scheme of analytical mechanics that Euler did so much to establish. In particular, if you have a conservative force, then any work that is done by pushing the piston downwards would be undone by then having to return it upwards to its original position. Same thing with a wheel. Any work that would be done when the parts of the wheel move in one way is undone when they move the other way and eventually returning to their original configuration. So even though I'm not an expert on the subject, I strongly suspect that Euler really had no interest in understanding the actual operation of a hydraulic pump, and this might be one of the reasons why he did not make a useful contribution to Frederick's project. But this theme that an active process, in this case, the pumping of water by a cyclical engine, is something that lies outside of the scope of the analytical mechanics that Euler did so much to establish. So let me talk a little bit more about systems out of equilibrium. And this is from the appendix to a paper that was published a few years ago with some collaborators, Robert Dolitsky and David Galvasser-Klimovsky. And you can think of two very broad types of systems that are out of equilibrium, which we call passive and active. So in a passive system, there is a disequilibrium. So somewhere you have, say, water in a higher reservoir, and then it can move towards a lower reservoir, or just in general energy or matter or heat. Somewhere has high free energy and somewhere has low free energy, and it flows spontaneously from high free energy to low free energy. And then that free energy difference can be dissipated in a load, making heat and therefore entropy. But there is no circulation in the flow. The flow just starts from high free energy and ends at low free energy. So I call that a passive system. But there are many active systems of interest in which you also have this equilibrium, but then you introduce a device that is capable of extracting some amount of work from that flow and extracting it in a cyclical way. So here it's represented as a turbine that is turned by this flow. And then you can use that turbine to move a pump in another part of the system. And that pumping can move the fluid from low free energy to high free energy, and then maintain a circulation in a closed circuit against the dissipation of the load. So here, the disequilibrium produces not just entropy, but also work. And that work in particular can be used to maintain an active circulation in a circuit. And you see here in parentheses under circulation, it says EMF. And this means electromotive force, which is something that I'll return to later when I talk, for instance, about batteries and solar cells and other active devices that are capable of maintaining a closed circuit current. So I will say a little bit more in a moment. Analytical mechanics was developed starting in the 18th century with Euler, Lagrange, and later in the 18th century Hamilton and Jacobi and others, does not apply to this kind of active systems. But there is a 19th century classical science of thermodynamics. In fact, I believe very recently in June, we celebrated the 200th anniversary of the publication of the document that created the science of thermodynamics, the essay by Carnot on the reflections on the motive power of fire and the machines proper to develop this power. And the science of thermodynamics starts with Carnot and is developed further by Joule, Helmholtz, Clausius, Kelvin, etc., is to a very large extent a science of heat engines. This is Carnot was initially interested in, was having a rational theory of the operation of heat engines. And heat engines are active systems. They're systems that can run cyclically and do work at the expense of this equilibrium, because there is some reservoir at higher temperature and reservoir at lower temperature. But the thing that must have struck many students over the course of the years when they've learned thermodynamics in university is that it is a science of heat engines, which are active devices, but it never treats their behavior as a function of time. So here the word dynamics in thermodynamics means power. Somebody who actually knew Greek explained this to me, but it's not dynamical in the sense that we're used to in mechanics of having equations of motion with time as the independent variable. So if you look even just at simply at the first law of thermodynamics, as it's usually presented now in textbooks, you have that the first term, which is the work done by the working substance in the engine, usually written as minus PdV, it is a mechanical work. So it is equal to a force dotted with a mechanical displacement. But we never deal in classical thermodynamics. We never really deal with that force. Certainly not as in terms of the Newtonian equations of motion. But the fact that you can go through a cycle, and at the end of the cycle, the heat engine has done some net positive amount of work, implies that the differential amount of work is not the work differentiable is not integrable. This is why it's written here with a letter delta. So people would say it's an inexact differential, but this implies that F is the force that's acting on the piston is not conservative, and it's actively not conservative, because this is why you have a useful engine. Now, this means that in an engine you can get what some authors call a self-oscillation. So you can get a periodic motion which is maintained by an external source of energy, here in this case, the disequilibrium between the hotter reservoir and the colder reservoir. But that external source of energy has no periodicity of its own, and yet it causes a periodic cyclical motion of the piston in the engine. So some authors call this a self-oscillation. So self-oscillation is an oscillation that is maintained, a periodic motion or variation that is maintained by an external source of power that has no corresponding periodicity. So this is quite different from any resonance phenomenon, such as we focus on in physics education. And there is a purely mathematical theory of self-oscillators, which was developed in the late 19th, early 20th centuries, but it's an entirely kinematic theory. So it's essentially an exercise in the theory of ordinary differential equations. And some French scientists, including Fabry, who's famous for the Fabry-Perot cavities, and especially Le Corbusier, who is not very well remembered nowadays, they said in the 1930s and the 1940s that there should be a connection between this purely kinematical theory of self-oscillators and the thermodynamics of engines, because engines, other motors in general, are precisely of this nature, that they run on a non-periodic disequilibrium, but they manage to generate the periodicity internally. And this is where I really step into this subject, because some years ago I became interested on this, and I ended up writing a review article, which is published in Physics Reports more than 10 years ago now, called self-oscillation. And this was really an attempt to take up this challenge, which had been raised by Fabrice Le Corbusier a long time ago, and which had really not been, not much had been done in this direction at all in the subsequent years. I think very few people paid any attention to this suggestion of really bringing in the dynamics in the sense of behavior in time into the description of engines, and not just of heat engines, but also of other active systems. So let me show you, this is also from a paper that we published some years ago with Robert Delitsky and David Goldwasser, on a simple model of a heat engine that runs on its own as a self-oscillator. So you need this equilibrium between the hot bath and the cold bath. And now we want to get this to run cyclically. We have a piston that contains the working substance inside of the cylinder. I've attached the piston to a spring in order to give a natural frequency to the motion of the piston. And then this equilibrium can be turned into a self-oscillation of the piston if you couple it in the right way. You couple the working substance in the right way to the hot baths. And there's a simple analysis. It's just an application of the first and second law of thermodynamics, which I like to call the Rayleigh-Eddington criterion. It was formulated in words in the context of thermoacoustic oscillations by Rayleigh. Eddington later independently wrote down essentially the equation that is on this slide in the context of the self-oscillation of pulsating stars, of Cepheid variables. But the point is that in order for this heat flow to encourage the oscillation of the piston, you need more heat to come in when the working substance is compressed and therefore at a higher temperature in its cycle. And then you need more heat to be rejected when the working substance is expanded and therefore a lower temperature in its working cycle. And the valves are drawn in this way. So when X increases, it compresses the working substance. The working substance of the temperature of the working substance rises, and the valve number 1 is open so that it can receive more heat from the hot bath, and vice versa. When X becomes negative, the working substance is expanded, its temperature falls, and then valve 1 closes while valve 2 opens, allowing it to reject heat into the cold bath. And this is simply an application of the laws of thermodynamics, but it begins to point towards the direction of what is actually happening in time. And if you look at the cyclical behavior of a heat engine, and for reasons that would take me too long to explain, I have long been an enthusiast of an old-fashioned toy called the putt-putt boat. So in a putt-putt boat, I showed a more detailed diagram of it in a moment. You have a small metal tank that is filled halfway up with liquid water, and the rest of it is a bubble of air and steam. And then the tank is connected to submerged exhaust. It's here it's two plastic straws, two bendy straws. This is putt-putt boat that I built myself from instructions on YouTube, and this is running in the bathtub in my house. So this is running as an active system, as an engine. The source of energy is this candle that is heating the tank, but it's called a putt-putt boat because it makes this periodic putt-putt noise. And what's happening is that the level of water inside of the tank is self-oscillating. It's going up and down. When it goes down, it pushes liquid water out through the exhausts, which propels the boat forward. Then when it comes back up, it sucks water back into the tank. But during that phase, the boat doesn't go back. It just stops for a moment. So this is why you see this jerky forward motion. And this works because there is a feedback between the rate of condensation of water vapor inside of the tank and the level of liquid inside of the tank. I became interested in the subject some time ago, initially out of idle curiosity. I looked at the literature on the subject, and I found that there were these old articles from the 1960s by two professors of engineering. I believe Finney was a mechanical engineer and Crow was a chemical engineer. And they write down equations, which I'll show in a moment, in order to explain how this works, how this feedback between the level of the liquid water in the tank and the rate of condensation of steam leads to this self-oscillation of the level of the water, which propels the boat forward. This, let me not get into the details, but this equations obey this Rayleigh-Eddington criterion because the most heat is rejected by a condensation when the working gas inside of the tank is most expanded. And so here the self-oscillating piston in the engine is the interface between gas and liquid inside of the tank. So here I've redrawn this pot system as a water pump. So here is the working substance is this bubble of air and steam inside of the tank. X is the level of the interface between that gas and the liquid phase. And I'm heating the tank with a flame, and I've added these two valves. So when X goes up, it sucks in water, and this valve will be open, this valve will be closed, so the water is sucked in from the lower reservoir. Then when X goes down, this valve is closed, this valve is open, so the water is delivered to the upper reservoir. And this is not hard to build in practice. So you can use this as a pump to move water from lower to an upper reservoir and store potential energy in this way. And you can describe the operation of this boat. So first we write down a Newtonian equation of motion for the level x. So if we were in equilibrium, oscillations about equilibrium would have a natural frequency. There's, of course, some damping. But then the force or pressure that acts on X depends on the amount of gas, in particular on the amount of steam that there is in the bubble. So if n were equal to n0, that would be the equilibrium position with x equals 0. But this n can change. It can change because you can increase the amount of gas by evaporating liquid water, and you boiling, this is this boiling rate B, but then you can reduce it by condensation. And the important thing, what makes this an active system, is that the rate of condensation depends on X. A simple reason to see why this is that when X goes down, it exposes more surface area of the metal, the wall of the metal wall of the tank, which is relatively cold because it's been in contact with the colder water. So when X goes down, there's more surface available for the steam to condense upon, and therefore the rate of condensation increases when X decreases. And you can show, do mathematical analysis, that if the derivative of this capital gamma with respect to x0 is large enough, then the equilibrium at x equals 0 and equals n0 is destabilized. So a small perturbation will cause a self-oscillation, which will grow until it's limited either by nonlinear damping or by the fact that it is outputting work by moving, in this case, by moving water from the lower reservoir to the upper reservoir. And so this combines, this dynamical description of a simple engine, this combines a Newtonian equation of motion with something that is not Newtonian. It's a kinetic equation for the quantity of steam. It's really a thermodynamic effect. And there's a feedback between the mechanical motion of the piston and in this case, the rate of condensation, which makes it into an active system. There's a more detailed description of how this works in a paper published some years ago with the same collaborators. But more recently, it became more clear in my mind that this is absolutely not something that you can put into the scheme of analytical mechanics. It's as we are taught that we are taught as physics students in university. So take the same equations. I can rewrite it as a system of three coupled first order differential equations for x, y, and capital N. Now, this means that this cannot be put into canonical form in the Hamiltonian formalism because canonical equations come in pairs. So you have to have necessary condition is that you need to have an even number of first order coupled differential equations. And here you have three. But also the first two, they are dynamical equations in the usual sense. They come from Newton's law. But the third one is of a different nature. The third one is a kinetic equation for the quantity of steam. So it's not Newton's law. I realized that this could be shown to be completely outside of the scope of analytical mechanics when I read about a very similar model for Schmidt trigger, which is an electrical self-oscillator, in an article on the thermodynamics of clocks by Milburn, published not so long ago. And then I went and looked into Whittaker's famous old book on analytical dynamics. And Whittaker says that all of the differential equations which arise from problems in the calculus of variation with one independent variable, in the case of classical dynamics, this would be time, can be expressed in the Hamiltonian form. This apparently is a theorem shown by Ostrogatsky in 1850. So the fact that the pot-pot-Bode equations cannot be put into Hamiltonian form tells me that they're in fact not obeying any Hamilton principle. They're not extremizing any action. They lie entirely beyond the usual description of analytical dynamics. That's in classical physics, but this is also an issue in quantum mechanics because, of course, the rules for quantization are based on the uh, canonical formulation of the corresponding classical system. In fact, if I remember correctly, it was from Whittaker's book that Dirac learned about Poisson brackets, which he used to formulate his rules for canonical quantization. Let me very briefly mention something else that we've worked on, which is a Quincke rotor. So a Quincke rotor is a dielectric cylinder, which is placed in a conducting fluid, and a constant voltage difference is applied to the edges of the fluid so that some current flows through the fluid. And when that current hits the surface of the cylinder, it can accumulate there, but then it can also discharge later. So this, under the right circumstances, this turns this constant applied voltage into a rotation of the electric cylinder. So you could call this a self-rotation of the cylinder in the conducting fluid. And this works because there's a feedback. There's a feedback between the turning, so the change in the position of the elements in the surface of the dielectric, and the charging and discharging by the current in the fluid. And in this reference, we show that you can write down the dynamics of this self-rotor in this way, which is also non-Hamiltonian. You might think that this is Hamiltonian because we have two first-order differential equations, but this set is a complex number, so it actually has those are two equations, one for the real part and one for the imaginary part. So this is also a non-Hamiltonian dynamics for the rotation. And I wanted to mention, there are things that are self-oscillating, there are things that are self-rotating. The math might look a little bit different, but they're both active systems. The important thing is that they can do work cyclically. So from the thermodynamics point of view, self-oscillation and self-rotation are not very different. But I wanted to talk for a moment about the Quincke rotor and the circulation in order to bring up this quote from the beginning of the Feynman lectures. So this was written a long time ago already, but I believe it's still true. So Feynman says that mentions that there are basic important problems in physics that are not yet resolved and that have nothing to do with finding new subatomic particles or new forces at the fundamental level. And he mentions the problem of circulating or turbulent fluids. And it's interesting to me that he says it this way because, of course, many of us have heard that turbulence is not adequately understood. But Feynman underlines that the problem begins with persistent circulation of the vorticity in fluids. So he says, for instance, that we can, if we look at in astrophysics, at the behavior of a star, we can compute when the plasma or the fluid in the star it becomes unstable and is about to start convecting, but the convection itself cannot be adequately calculated. We still have trouble understanding how supernova explodes, and even more down to Earth, we have a lot of trouble understanding the weather, starting from the equations of fluid dynamics. And as Feynman, I think, here emphasizes correctly, the main reason, certainly one of the principal reasons for this difficulty, is that all these systems have persistent circulation of flow, which we have trouble describing with the techniques that we're trained in physics. And I think this really is because all of these are active systems. Let me mention very briefly that the problem, so you don't need to go all the way to turbulence. The problem is already there, for instance, in the theory of aerodynamic lift. This was an article published a few years ago in Scientific American on the enigma of aerodynamic lift. The subtitle is "No one can completely explain why planes stay in the air." And the problem again is circulation. So here's a diagram that I've taken from the textbook on the physics of energy by Jaffe and Taylor. So here initially you have an ideal flow around the wing, around the airfoil, and there's no circulation around around it. You could show then there's something called the Kotta-Joukowski theorem that lift acting on the wing is proportional to the circulation around its surface. So if there's no circulation, there's no lift. So the wing needs to develop some circulation because of conservation of angular momentum. There's a counter circulation that is shed as a vortex that moves down in the flow. And usually what people do is they impose a condition called the Kotta condition that the flow around the airfoil remain attached to the top part until it reaches this sharp trailing edge at the back. And that condition fixes the circulation, but you're not really calculating it. You're just imposing it by hand. In fact, this condition is not always physically satisfied. If the angle of attack of the wing becomes too large, you develop a serious problem called stall, which comes from the flow separating, the airflow separating from the surface of the wing before it reaches the trailing edge. And this is something else that so you might have seen. So this is instead of this complicated airfoil, this is just a cylinder in the middle of the flow. And in this case, vortexes are repeatedly shed, but first you shed a vortex in one direction and then in the other direction. So this leads to not a constant lift force in one direction, but a force that alternates up and down. So this is a clear instance of self-oscillation, but it's one that I don't think is very easy to understand theoretically with the tools we have. But this is similar to the problem of understanding lift. And I took this from a book that is referenced in the Scientific American article, where the author MacLean mentions that often what is done in the theory of aerodynamic lift is to idealize the flow. So you write down the velocity as the gradient of a scalar potential, but this forces the flow to be irrotational because the curl of any gradient is zero. So this wouldn't give you any lift. So what is done is to introduce a branch cut, taking this to be the plane, treating it as a complex plane, a branch cut, and then there's a discontinuity in that branch cut that you cannot compute. But that discontinuity is what gives you the circulation. And then you can impose the Kotta condition. Imposing the Kotta condition that the flow is separated, the trailing edge fixes the discontinuity along the branch cut, and therefore fixes the um, the circulation. But you're not really calculating that from the laws of hydrodynamics. You're putting it in by hand. So that's another glaring instance of something that in practice is we have mastered for a while, which is heavier than air flight. But the question, the theoretical question of how the wing generates lift is in fact not resolved because it is an active system, or as the point that Feynman emphasizes, because it depends on this persistent circulation of a fluid. I've had an amateur interest for a while in economics, and particularly in the communication that there has been between theoretical economics and physics. So I was interested to learn about this guy, Nicholas Georgescu-Roegen, who's from Romania, an economist, but he did most of his career in the United States. And this is from a retrospective article published after his death. It says that one of the main themes of Georgescu's writing was his protest against the use in economics of models inspired by Lagrangian dynamics, which assumed that economic agents obey forces of conservation deducible from a potential function. So if you assume that the behavior of consumers is maximizing some well-defined utility function, then you can describe that the economics as a process of optimization under budget constraints. But the question is this really true? Is this really how things work in the real world? I was very interested to learn that Georgescu started out as a statistician, and for his PhD thesis, which I think was in Paris, he developed a method for trying to locate or to find cyclical components in economic data. So this was at the time of interest for boom and bust macroeconomic cycles, where you could look at the data and identify that some part of it was a regular cyclical component superimposed in a bunch of noise and other things. So it's kind of a self-oscillating problem. But he later went in this direction of, questioning whether the behavior of economic agents could really be, in general, described in terms of optimization. And later on, he tried to bring in insights from irreversible thermodynamics into economics. And I think the reason why this was not more fruitful is because it turned out that this problem of irreversible thermodynamics in the dynamical sense was too weakly developed in physics itself. This is an article by Paul Samuelson, a very well-known Nobel Prize in economics, where he talks about the same problem, the problem of the integrability of consumer behavior, where you can describe the behavior of consumers as if they were optimizing some function of the amount of the various goods and services and on their prices under a budget constraint. And he mentions this. So Gustav is his name for somebody whose behavior is not integrable. And he says that you can take Gustav along in this space, x1, x2, x3 are quantities of goods. You can take him along in different curves. He's equally happy to have. So he can give up some x2 in exchange for x3 and remain equally happy. So you take him along the indifference curves, but then when you're supposed to return to the starting position, it turns out that you moved up in the axis x3. So now after this process, he is satisfied with a larger amount of x3 than he was at the beginning. But so question is, this seems economically irrational, but does this happen in practice? I would say that it does in efficient markets. But what interests me most now is that this really looks very analogous to what happens in an engine, in an active engine, which is that you go around in a cycle in the degrees of freedom of the engine itself. But at the end of that, you've done some amount of work. So you've acted on a load, you've raised a weight, or you've raised water from the lower reservoir to the upper reservoir. So you've done something. And then Samuelson mentions that somebody with this kind of non-integrable behavior can be cheated. You can take them along passive indifference, but every time you go along one of the cycles, they have less and less, say, of X3. And I think this is something that's also worth thinking about in the context of the theory of economics and of finance, whether it's possible to extract profit cyclically by, say, a rebalancing strategy from an inefficient market. But anyway, the point is that there's there's a very closely related problem in economic theory to the one that I'm trying to emphasize in physics. And Samuelson, in his very famous book, Foundations of Economic Analysis, based on his PhD thesis, he also says at the beginning that even in the simplest model of business cycles, in an endogenous business cycle, a boom and bust cycle in the economy, there is not enough symmetry, which in my language would be a form of self-oscillation. There is lacking symmetry in the conditions of equilibrium, so there is no possibility of directly reducing the problem to that of a maximum or a minimum. So a model of an endogenous business cycle falls outside of the whole scope of optimization on which most economic analysis is based. But now let's go back to physics, and let's go back to something very fundamental, which is the concept of electromotive force. So this goes back to Volta, who invented the first electrical battery in 1800. And it was Volta himself who introduced this term EMF, electromotive force, in order to describe that whatever it is that is separating opposite charges against their Coulombic attraction and keeping them separated, so that when you release them, they don't just recombine, but they go all the way around in a circuit. So an EMF can drive charge along a closed circuit against resistance. It's therefore an active process. I'm sure many students have been confused by this concept, starting from the fact that it's called a force, but it doesn't even have units of force. It's really the integral of an active force per unit charge. But I think the reason why this has not been corrected is because there's a fundamental conceptual issue which has not ever really been adequately dealt with, precisely because of the active nature of the process that causes this phenomenon. Physicist Peter Heller suggested that instead of saying EMF or electromotive force, we should say EMP for electromotive pumping, because what is really, so this is something that's happening at the interface between the electrode and the electrolyte in the battery that is really pumping charges. So it's moving charges against the local averaged electrostatic field. And this active pumping, it can build up potential difference, what's usually called the voltage of the battery. So you can, let's go back to the hydraulic pump. The hydraulic pump can build up potential energy difference between the water in the upper reservoir and the lower reservoir, and you can measure the strength of the pumping based on how much potential energy is built up in this way. But that potential energy stored in the reservoirs is not the same thing as the action of the pump that has moved water against the gravitational potential. In a similar way, you can measure the strength of the EMF by the voltage that it can build up between the terminals of the battery, but the mechanism by which it builds up that potential difference is something else, and it is an active process. So it turns out that if you look into the literature and the history of philosophy of science, which I did at one point, you will learn that the entire 19th century and part of the early 20th century were I wouldn't say consumed, but during that whole time, there was an intense ongoing debate about where and how Volta's EMF acted in a battery. There are two main schools of thought called the contact theory, which said the basic thing is that you have two different metals, say zinc and copper, where electrons have different potentials. So electrons want to go from the metal where they're at a higher potential to the metal where they're a lower potential. Versus the chemical theory, which said that really the essential point is the chemical reaction going on in the interface between the metal and metal electrode and the electrolyte, and that is really what is driving the this pumping of charge that builds up the voltage of the battery. And this debate involved basically everybody who was anybody in either physics or chemistry in the 19th century and even into the early 20th century. Here are some names. I learned about this originally from this article by a Danish historian of science. I believe that this surname is correctly pronounced Krau in Danish. But this debate was never really resolved satisfactorily. It just petered out after a long time because of several reasons. One of them is that batteries were optimized by trial and error in the same way that other energy devices like solar cells, for instance, have been optimized by trial and error. And also the laws of, over the course of the 19th century, the laws of thermodynamics were clarified, and it was seen that whatever it was that was happening within the battery obeyed the laws of thermodynamics. So you had a budget for how much energy you could get from a voltaic cell. But also eventually people sort of, I suppose, got tired of arguing about this. And then in the early 20th century, at least for theorists, there were more exciting things to worry about, like relativity and quantum mechanics. But this is a quote from an article by Hasuk Chang, who's a professor of history of philosophy of science at Cambridge, where he emphasizes this, that it says the standard theoretical treatment of electrochemical cells in physical chemistry textbooks occur under the rubric of thermodynamic equilibrium, and they focus on computing the steady state half cell voltages from the Nernst equation. For anyone wanting a rather mechanical or causal story of how free electrons start getting produced and get moved about, so a really dynamical description of what's happening in the battery, the modern textbook theory is a difficult thing to apply. I go a little bit further and say that it's something that is not explained in the textbook theory. And I like this very much, right? It was a great encouragement to me when I realized that the problem was not with me, that I had not adequately understood the discussion of batteries in the textbooks when I took elementary electromagnetism in university, that this was really a problem that had not been theoretically solved. It's another article that I like by the same author, by Hasuk Chang, called History and the Philosophy of Science, a continuation of science by other means. Riff on the famous quote by Clausewitz. But this is really what I would like to get out of HPS in this context, that you need, so we're too busy as practicing scientists to even be aware of the fact, say, that something as everyday as a battery is what seems to have been so well mastered from a technological point of view, presents interesting theoretical questions that remain open. It requires something like HPS in order to make us aware of these blind spots in our training in theoretical physics. But just to emphasize that this point about not really fully understanding what's going on in the battery is not just something for historians and philosophers of science. Here's an article published not so long ago in a very prominent journal in energy science, where the authors say that despite remarkable achievements in developing lithium-ion batteries over recent decades, many fundamental scientific issues underpinning lithium-ion batteries are far from being adequately understood. And in this article in particular, what they emphasize is the presence of this slow self-oscillations that are seen both during the discharging and the charging of the lithium-ion battery. Here, they even draw a little heart. See, describe this self-oscillation as a kind of heartbeat inside of the battery. And some years ago, with some of my usual collaborators, but also with Liz van Houw, who's an experimentalist. This is a theoretical paper, but it has some input from an experimentalist who is an expert on things like impedance spectroscopy for interfaces between surfaces. About this, and what we're proposing is that there really has to be an active dynamics, self-oscillation at the interface between the electrode and the electrolyte in order to explain the pumping of charge that builds up the EMF of the battery. I was shocked when going back to the history of science. I was shocked when I found at one point that the man widely regarded as the founder of electrochemistry, Sir Humphrey Davy, had said something that was similar to what we're saying, that there has to be a self-oscillation in the battery in order to explain the EMF. So this is from an early work by Davy, where he says that proposes that the electrical equilibrium may be conceived to be alternately destroyed and restored, the changes taking place in imperceptible portions of time. So he's saying that there is a cyclical self-oscillation in the electrode-electrolyte interface in the battery. It's just that it's so fast, and presumably its amplitude is so small that it has not been directly observed. And later on, in 1926, he said something similar in even more detail, that the equilibrium broken by the contact of the metals is restored by the chemical changes so that a constant circulation of current of electricity takes place. So I think this is true, that Davy believed that it was at least likely that there was a pumping dynamic, so self-oscillation hidden inside of the battery that had not been identified. This was insight that I think was lost later as physics and physical chemistry moved in a more analytical direction, where it's harder to even fit in this picture of active pumping. But the point is, pumps have moving parts, and they're cyclically moving parts, and this is what's missing. And this is not just for the battery. This is an issue that we've also pointed out in the context, for instance, of the theory of solar cells and fuel cells and other energy generators. But evidently, another place where active dynamics is extremely important is in living systems, in biophysics. So here, also continuing in this vein of bringing up anecdotes from history, and also because I was interested in whether I could learn a little bit more about what Davy thought of this in this context, I looked up, I think this is the last volume of the collected works of Sir Humphrey Davy. This was edited after his death by his brother, who was also a scientist. And I believe that this is a note that was added by his brother to the text of the last article that I cited in the previous slide. And it says, the cause of voltaic electricity, as well of every other kind of electricity, is still a vexed question, quaestio, etc., and is likely to remain such. The further inquiry is extended, the more mysterious the subject appears, not unanalogous in this respect to the principle or cause of life. So in living cells, you also need to have active pumping of charges in order to be able to build up potential differences that can be used to power the processes that are going on in the cell. And evidently, this is mostly an electrical, or almost entirely an electrical process that must have some analogy to how charge is pumped in a voltaic battery. And my attention was also piqued by learning that Sharon Ruston, who's a professor of humanities at university in Britain, has been the editor of the collected letters and notebooks of Sir Humphrey Davy, but she's also written a book on which were the scientific sources that Mary Shelley used when she composed Frankenstein. Apparently, one of the main ones was precisely Humphrey Davy, but I have not been able to get my hands on this book. This is something that I would like to do whenever I have enough time to dedicate to that. But let me, continuing in the line of biophysics, tell you, also emphasize that something that looks so trivial, so basic as the question of how does sap rise inside of a tree? What's the mechanism by which sap, which is mostly water, goes up in a tall plant, is an open question. For a long time, the more widely accepted view is that this is just a hydrostatic process driven by capillarity and transpiration pressure. But this authors pointed out in this article from not that long ago that this cannot make sense because this is an experiment that you can do easily. If you take a closed bottle and attach it to a hose and you keep it filled with water, if you raise the bottle more than about 10 meters, the pressure minus pressure drop minus rho GH and the bottle is large enough that the pressure inside of the bottle is such that the water begins to boil at room temperature. So, you know, there are certainly trees that are taller than that. So how come the water and the leaves on the top of a tall tree, why don't they boil away because of this depressurization? And what some authors, including the authors of this paper, suggest is that there really has to be an active pumping mechanism associated with the living cells that is responsible for this pumping of upwards of the water of the sap in the tree. So even this is an open question. Let me also mention that the oldest electric phenomenon ever reported is triboelectricity. So the ancient Greeks already knew that if you rub, say, a piece of silk against a piece of amber, then you can take the amber and the silk and attract little bits of straw with it. It behaves in various interesting ways. Now we would call this triboelectricity, so the accumulation of static charge from the mechanical rubbing between two different materials. And it turns out that this is, in fact, this is the source of the term electricity, because electron in Greek means amber, and amber is one of the first materials in which this effect was observed. But it turns out that there is not an adequate theory of triboelectricity. And this is something that I worked on with my collaborator, Robert Rylitsky, some years ago. So here's a very minimal triboelectric generator where you have, this wouldn't be useful as a generator, but it's the simplest setup that will give you an EMF from mechanical friction. So you have an inner cylinder of a material A and an outer hollow cylinder of a material B. And as the cylinder A spins with angular velocity omega, the rubbing between these two different materials can create an electromotive force that can move charge along a closed circuit. But it's clear that this EMF cannot be understood in terms of Maxwell-Faraday law, because it would require a linear, and a constant EMF would require a linearly growing or linearly decreasing macroscopic magnetic flux through the circuit, something that's obviously not present. There might be some small magnetic fields in here, but they're not coherent, and they're definitely not, the total flux is not linearly growing or decreasing in time. And also it's clear that this is a irreversible process, because in a Faraday inductor, if you reverse the turning of the coil, you reverse the EMF. But here, if you reverse the direction in which you turn the cylinder A, that doesn't matter at all. The direction in which you rub is not important. What's important is the difference between the two materials that are being rubbed together. This is clearly an irreversible process. And we wrote an article some years ago, which was published in Fistriff Letters, and it even got a bit of attention in the scientific press. It's a picture of me, it's my collaborator Robert Elitsky, holding a bust of Thales of Miletus, because it was a gift from me, because Thales was the first person who was recorded as having commented on the triboelectric effect, but also as a mathematician. He did shown up in earlier work that Robert had done when he was mostly a mathematical physicist. But here again, what is key is to understand this kind of processes as active pumping. So in the last few minutes, I would like to comment on how this problem appears in the context of statistical physics. So statistical physics was developed in order to explain the laws of thermodynamics, but it was developed for systems that are in macroscopic equilibrium by Maxwell, Boltzmann, and Gibbs in the 19th and early 20th century. Later, theoreticians have worked to extend this beyond equilibrium, but the work that has been done really applies only to systems that are either fluctuating stochastically about equilibrium or are relaxing in a purely dissipative way, what I would call a passive irreversible processes towards equilibrium. So here, the main results, which you will find in any textbook on statistical physics, if you go to the chapter on non-equilibrium processes, will be the Einstein and Smoluchowski theory of Brownian motion, fluctuation dissipation theorems, and Langevin equations. And I think that these tools are all properly applied only to passive processes, so to irreversible processes that give only entropy, not work, and that they've been abused in order to try to apply them to systems that are that are actually active. There's large literature nowadays on, for instance, on what's called active matter, which I think is not. It doesn't start at the correct place. You have to really take into account the fact that to describe an active system dynamically, you have to step outside of the formulation of analytical mechanics that we have started with from in our education and in our work for a very long time as physicists. And when you talk about non-equilibrium thermodynamics modernly, usually one of the main things that people will discuss are the Onsager relations due to Lars Onsager, who worked on this starting in the 1930s. I think his interest initially was to understand thermoelectric generators. But in this formulation, all of the currents and forces are given by gradients of state functions, of thermodynamic potentials. So you have the problem that by the fundamental theorem of calculus, if you integrate the gradient of something along a closed path, you have to get zero. And in active systems of interest, in which the pumping is present, there are circulations of current or flow in cycles. These persist against dissipation. So what is needed in the case of active systems, which is really a theory of pumping, falls outside of the scope of this kind of description. So often in this analysis, for instance, you will find the EMF of an active system, electrical system, by assuming that it's in a steady state, so that the amount of energy that is being pumped into the circuit is the same as is being pumped at the same rate at which it's being dissipated by a load. And then what you actually calculate is the dissipated power. And this is also related to the failure of the attempt of Prigogine, for which he even got the Nobel Prize in Chemistry in the late 1970s, of generalizing this kind of Onsagerian analysis to nonlinear systems in order to develop what he hoped would be a general theory, what he called dissipative structures. But this is I would say that now most people would accept that this effort was unsuccessful. So let me not say a lot about turbulence. Turbulence is a little bit hard to define in detail, but following Stewart, I will say that you can identify its basic symptoms. So turbulence is disorderly. So there's a part of the variation in the velocity field that is not periodic and that cannot be predicted in detail. So it must be treated stochastically. But two other basic points is that turbulent flows have circulation, so they have vorticity, and that this leads to an efficient mixing of the fluid. In fact, the reason why you stir your coffee and to dissolve the sugar in the morning is to set up a turbulence that will mix the fluid with the sugar efficiently. So I think many people are well aware that we don't really have a theory of turbulence. This is a great challenge in theoretical physics. But let me just make some basic observations about this. One of the very important features is that this irregular stochastic oscillation variations in the velocity in the turbulent flow are not Gaussian. Taking this illustration from an old instructional video by Stewart. So here he shows a measurement of the velocity of a turbulent flow. So that could look Gaussian, that could look like white noise. But if you look at the first derivative, then it definitely doesn't look Gaussian. You realize that it's very intermittent. And there's a huge literature on how complex systems often don't look Gaussian. People often emphasize the fact that they have heavy tails, right? That extreme events are significantly more probable than they would be for a Gaussian system. For instance, you can look at variations in the prices of stocks in the stock market and find this. But I think I strongly believe that this is closely related to the fact that many of these systems are active. And turbulence certainly is an active process because it fundamentally involves this circulation of fluid, which, as Feynman emphasized, is where he really sees the heart of the problem that needs to be addressed. And I should mention that in the field of quantum optics, for instance, you can diagnose the transition between thermal radiation, which is a passive process, and lasing. Lasing is an active process. So lasing, generation of laser light, it's thermodynamically irreversible. So the crystal of the laser heats up when it's operating, but it doesn't only produce that heat. It also produces a non-thermal radiation, which you could consider the work output of the laser, considered as a heat engine. And when this happens, you can figure out whether you've turned on lasing by seeing this transition from Gaussian to Poisson statistics for the photon. So I think one thing that is very interesting and that needs to be studied in much more detail is this how you can statistically describe active systems. So this is from a paper that I read some years ago when I became interested in the theory of Josephson junctions, which is something that I won't have time to mention here. For instance, here they show this phase diagrams, and here on the right is the phase diagram for thermal radiation. So you have a Gaussian distribution around the origin in the phase space. But when you have a laser, you have a limit cycle, and the noise is distributed along this cycle. So even the topology of the distribution has changed as you turn on the active dynamics of the lacing, and this must be associated with the change in the statistical properties and the fact that that somehow active systems are often evading the central limit theorem. So this is why they do not look Gaussian. So I would like to emphasize that there's been a lot of talk in recent decades about complex systems and science of complex systems. In fact, the Nobel Prize in Physics for the year 2021 was awarded for, quote, groundbreaking contributions to our understanding of complex physical systems. one of the parts, one of the works that was rewarded by this Nobel Prize concerned models of the climate of the Earth as an Ornstein-Uhlenbeck process, which is basically just Brownian noise with a drift. And I've taken these quotes from the official scientific background of the Nobel Prize, where they're describing this work, and they say that one of the results is that on the decadal timescales of relevance to humans, evidence from climate data is consistent with a memory effect in the ocean. It's effectively infinite, much longer than the timescale relevance to humans. So you have to put in this enormous memory effect in the ocean in order to try to accommodate the data. And then later they say the basic observation that a data record can be non-stationary, having a growing variance and a difficult to measure mean, are amongst the basic tenets of climate variability emerging from Hesselmann's work on the analogy with Brownian motion. Okay, so my take on this would be that if you look at the data and you find out that if you, by modeling as a Ornstein-Uhlenbeck process, you find that you need this huge memory effects. It's not stationary. The variance grows. The mean is hard to define. What this tells you is that you're not really looking at an Ornstein-Uhlenbeck process. You're looking at something different. And definitely, certainly, the climate is an active dynamic. It's not a passive dynamic of the sort that would be adequately described as Brownian motion or Brownian motion with a drift. And I think that my own view is that too often complexity and labeling of systems as complex has been a cop-out that really masks the fact that we don't have adequate tools to treat rigorously active systems. So this is a cartoon that I saw some years ago on the door of Paul Spanos, who's a professor of mechanical engineering at Rice University. The father is saying to the son that that's not white noise, that is the ocean. I think this is precisely the trouble here, that something like the ocean is an active system, and it's not adequately described with the kinds of tools that have been developed for passive non-equilibrium statistical physics and thermodynamics. So in the few remaining minutes, let me just very briefly give you an overview of recent work in which my collaborators and I have tried to apply this kind of thinking to cosmology. And I'll say why I think this is a fundamental issue in physical cosmology. And this is also a return to my own roots in high energy physics. So many of you, I'm sure, will have at least heard of black hole thermodynamics, developed in the 1970s by Sadowicz, Bekenstein, and Hawking, among others. And even though this is not usually stressed, it should catch your attention that this implies, if you believe in the Hawking temperature of a black hole is a solution to the Einstein field equations, which are classical field equations, like the Maxwell equations for electromagnetism, except more complicated because they're highly nonlinear, whereas Maxwell's equations are linear. But this means that a solution to a classical field equation has thermal properties. So how is that possible? This definitely would not be possible in Maxwell's equations. So any solution to Maxwell's equations describes a reversible, thermodynamically reversible process, and it doesn't have any temperature or entropy or anything like that. So the fact that solutions to Einstein's field equations have thermal properties already strongly suggests that behind this classical field equations, there should be a more fundamental quantum theory that might not live in the same space-time in which Einstein's equations are formulated, but where it's possible to count entropy. So to count entropy, you look at a macroscopic configuration and you count how many different microstates are compatible with the macro state, in this case, the macro state described by the Einstein field equations. So, but that counting of entropy, which you need in order to have thermal properties for your solutions, points to some underlying theory which might live in different space-time. The space-time itself might be somehow emergent from the underlying quantum theory. This is not even though this is not the way that this is usually presented to students, this is not a controversial idea. There's this large collaboration with the Simons Foundation called It from Qubit, which is based on this kind of idea. But it was realized in the 20th century that the universe is expanding. And already in 1939, Schrödinger wrote an article pointing out that if the size of the universe is growing and accelerating, the rate of growth of the size of the universe is accelerating, this will cause what he called alarming phenomena of particle production and annihilation, what we would now call cosmological particle production. And the reason is that if you write down the Fourier expansion of a field, you have terms with positive and negative frequencies. When you quantize the field, these become creation and annihilation operators, but then an accelerated expansion of the space will mix this term. So we'll mix the creation and annihilation operators. So this would cause particles to be produced and destroyed by the mere expansion of the universe. And much later, in 1977, Gibbons and Hawking calculated that in a de Sitter space, so in an exponentially expanding space, the space will have a temperature, and the temperature is proportional to the Hubble parameter h. H is a dot over a, where a is the scale factor of the universe. So in an exponentially expanding, i.e. de Sitter space, h is a constant. And this problem of the thermodynamics of the de Sitter space has remained quite contentious and poorly understood for many years. In fact, some very important theoretical physicists have commented recently on this problem. In our case, what we're really interested in is taking tools from quantum thermodynamics, from the theory of open quantum systems, and using them in order to describe the expansion of the universe explicitly as a thermodynamically irreversible process. And I think that the consequences of doing this are quite interesting in cosmology. So, for a while now, since 1981, great majority of cosmologists physicists have accepted that very most likely the universe began in a very brief phase of exponential expansion, the Sitter phase that ended after a short amount of time. This is usually called inflation, and this solves various problems that had been outstanding in cosmology for a while, while also accounting for the primordial perturbations that later become slightly overdense regions that seed the formation of galaxies and galactic clusters. But even though this is very widely accepted, I like this quote from a classical text by Colvin Turner, where they say that inflation is a paradigm in search of a model. So even though it's widely believed that this happened, how exactly, what exactly drove inflation, how it ended, etc., are questions that remain highly contentious. The most popular way of doing this nowadays is by saying that there is this field called the inflaton, not otherwise observed, and that it has a very particular potential. You have to, in order to get this to behave the way you want it, you need to engineer this very peculiar potential. So the field starts with a value at a part where the potential is almost flat, so it rolls down very slowly down this nearly flat part of the potential, and that's inflation. Inflation has to end, so this is engineered into this picture by having the potential steepen suddenly, so that inflaton rolls down much faster, and this is the end of inflation. But then later you need to take all of the energy that was in the inflaton and put it into the ordinary particles and radiation that we see today filling the universe. And this is usually described by this rocking back and forth of the inflaton at the bottom of its potential. And since it's coupled to the other matter and radiation fields, then this rocking motion is damped, and the damping is associated with the production of these other particles that reheat the universe. But I think this is quite an artificial picture, and also I think this goes back to uh, problem in our training, in our education of theoretical physicists, that we're much too eager to try to describe processes by invoking potentials. And I think in fact, only quite simple, boring things in real life are adequately described by potentials. Really interesting process, certainly active processes, are not described by by potentials. So when you have to engineer a potential function in this very particular way in order to get what you want, I think this is suspicious. But I also there are various problems, open problems in cosmology, in inflationary cosmology. Generally, these models require you to choose a very, very special initial state for um, pre-inflation, so very low entropy initial state. There's this issue of understanding why inflation ends suddenly after the size of the universe has expanded by a factor of at least e to the 60. People say is having at least 60 e-folds. Then you have to explain how the energy of the that drove the inflation is turned back or turned into thermal radiation, filling up the universe with its absurd entropy, but not just entropy, because at the end we want a state that is not just a pure equilibrium state. We want something that that is sufficiently far from equilibrium that it will allow the formation of structure and the appearance of galaxies and stars and planets and us and so on. So you don't want just a thermalized gas to come out of this process. And also there's the question of why, so even though inflation stopped recently, the expansion of the universe data indicates that it's started accelerating again. So it seemed to be entering a new de Sitter phase, but at a rate of expansion that is much, much, much slower than the one in the initial inflation. So what my collaborators and I have been trying to do recently is to take the techniques of quantum thermodynamics based on the theory of open quantum systems and apply them to the early universe to describe the early universe with these techniques as an irreversible active dynamics. And I think this has important consequences for these various open problems in cosmology, which I won't mention in too much detail because I don't want to extend far beyond an hour and a half right now. But I'll give you the references in a moment. And I think we're not the only ones who think that inflation works along these lines, that it's associated with an instability of the de Sitter phase itself, and you don't need to invoke this inflaton with a very particular potential. And somebody who I think has been advocating this sort of point of view for a long time is Polyakov, a very distinguished Russian-American theoretical physicist. And here, this is a variation by Polyakov on a little poem by Nabokov, which is the stimulated emission of cosmic media affords a fascinating occupation for proletarians and lords. Okay, so let me not get into the full details, but let me just say that the point of this work is that we draw an analogy with an active process called superfluorescence. Well, actually, most people call it superradiance, but I prefer the term superfluorescence. There's something else called superradiance that I'm also interested in. And in superfluorescence was a process predicted by Dickey a while ago. And if you have the way it works, you have some large number n of two-level atoms, two-level systems with some splitting omega sub a, and you take them to be independent of each other and interchangeable, but they're all collectively coupled to a single electromagnetic mode. For simplicity, we can do this at 0 temperature. And then you take that nearly all of them are initially excited, but unlike in normal fluorescence, where they will just begin decaying to their ground state at random times, and then you get an exponentially decaying light curve coming out of the system, in this case, when they're all collectively coupled to a mode, they stay in their excited state for a while, and then very suddenly they all start decaying in unison, and they produce this narrow pulse of coherent light. So this was predicted by Dickey in 1954. This is an illustration from a review article by Gross and Haroche. This is a little bit like a laser. From my point of view, the important thing is that it's also an active process. So it generates, it's an irreversible, thermodynamically irreversible process, but it produces non-thermal radiation, which you could think of as a work output of this active dynamic. And this was predicted by Dickey at around the same time when people began working on masers and lasers. And I believe that Dickey later also, in fact, got the patent for the first IR laser. So this he was definitely an expert in this kind of process. And Dickey also, of course, had a strong interest in cosmology. Dickey himself called this process super radiant, but I prefer the term superfluorescence in order to not get confused with something else that is called super radiance in the literature. And this is a plot of what we get when we do the analysis for the open system in an expanding in a de Sitter universe. You get something like this. So rho ds is the energy density of the empty space-time. So it remains constant for a while, which is at the Sitter phase. So this is inflation. But at some point, it begins decaying on its own quite quickly. And this is associated with the production of regular radiation. And matter, ultra-relativistic matter, rho sub r. So inflation ends, it ends naturally, it ends itself, and it ends producing a large amount of, it ends by producing regular matter, radiation. So this naturally reheats the universe, and this has not been necessary to invoke any kind of inflaton field or inflaton potential. Another thing that is very important is that because this is thermodynamically irreversible, even though CPT is a good symmetry, charge parity time conjugation is a good microscopic symmetry, macroscopically it is broken because since you're out of equilibrium, you're not obeying detailed balance, and this makes it much easier to explain why this process of producing matter would generate more matter than antimatter, which is a problem that is known in theoretical physics as baryogenesis. So this work is contained in a paper that was published last year with Robert Dalitsky and Gabriela Barenboim in PRD. This is an accompanying shorter letter that focuses on the consequences of this for inflation. And we've been working recently on how to incorporate naturally a model of spontaneous baryogenesis into this kind of approach. But the issue here is really to describe the early universe, not just as thermodynamically irreversible, which is, I think, something that everybody would agree has to be the case. Because in fact, you need to produce the observed entropy of the universe as a result of inflation, but also as an active irreversible processes that leaves behind also non-thermal radiation, which allows interesting things to develop in the universe later on. Okay, so as not to abuse your patience too much, let me finish and summarize the main ideas that I've been trying to get across in this rather broad talk. So my key point is that many interesting systems in technology, in life, in many areas of physics are active, but this constitutes a blind spot in theoretical physics. We really have lacked, they fall outside of the scope of analytical dynamics, analytical dynamics was really developed for purposes of celestial mechanics, mostly in the 19th century, and celestial mechanics is controlled by gravity, which is a conservative force. But the issue here goes even beyond the problem of dealing with non-conservative forces macroscopically. As I've tried to emphasize, the active systems, when you try to describe them realistically and combine them with thermodynamics, you realize that they don't fall into the scheme of analytical mechanics at all. Also, in my humble opinion, the issue of understanding activity is more fundamental and should be better posed than the vaguer but more popular issue of complexity. Because in some sense, you could think of an ideal gas as a complex thing because it has so many molecules, yet it's very easy to describe because it's entirely passive. But the things that I think are really a challenge are the systems that are active, including things like understanding the mechanism of pumping of charge in a battery or in a solar cell, or the mechanism by which lift is generated in the wing of an airplane. And there are many active systems of interest in which the dynamics of pumping, so pumping is an active process, it has moving parts in general, but people don't see that dynamics. It has remained invisible for various reasons. In the case of the battery, it might be, as I said, because it's very fast, and also because there's a large surface area, so the amplitude of the oscillation of the double layer in between the electrode and the electrolyte is quite small, because the smallness of the amplitude is made up by the largeness of the area. So this makes it difficult to see, even though there's in fact a lot of experimental evidence about various self-oscillations in batteries and solar cells and other energy devices. But they have not been interpreted, I think, as being a fundamental part of the pumping mechanism of the charge. This is a very broad issue which has consequences, I think, important consequences in many areas of physics, ranging from biophysics to cosmology. And this is really essential for the development of what has become a very active field of research in recent years, which is quantum thermodynamics. I talked mostly about classical physics, but this problem of describing active dynamics is, of course, also present in quantum physics. And if you look at microscopic systems, or you look at cosmology or things like that, you really need to consider the problem from the quantum at the quantum level. And at the very end, although I did this very briefly, I mentioned recent work in cosmology, but I would just like to say that I think that the grandest of all the active dynamics is the beginning of the universe, because it is clearly irreversible, but it's also not passively irreversible. It leads to something that is not an equilibrium. It generates non-thermal radiation, like work, which is what allows us to be here wondering about this kind of phenomena. So this is really, I think, a very important, very broad challenge in theoretical physics. And it will take a considerable amount of effort, because it requires us to rethink many things from a fundamental level. And one of the areas in which I think we can get some help in this direction is from the awareness of people who work in the history and the philosophy of science, of the fact that there are problems that we've been taught as physicists not to think about, that remain theoretically unresolved. Thank you very much for your attention, and I hope that this has been of some use to you.